All right, we're back. So remember during class I mentioned that I didn't know how to test the area business. Kepler is, let's take a look first of all. We'll do it by the numbers. I remember my volleyball coach always. So, width, right? So we have all these definitions and, let's see, and 0.5 is at the perihelion. So helion is the smallest distance. Okay, so Kepler's first law says that it's an ellipse with one of the um, um, with the sun at one of the foci. And if that's all true, then and in fact for any, and so it's actually a little bit more than this because I need to for now I'm going to leave the lab manual as it is, but this x squared over a squared plus y squared over b squared is from the center. So I need to construct that equation, but because it's from the center and my data is generated from one of the focal points, excuse me, I have to displace the x values each time. And that's simply by little c, which is up here in Q3. And since it's, I have to subtract it because each of the x values is going to be from there. Let's see, if I shift over, I've shifted over to the left. No, I shifted, excuse me, the plot is shifted to the right, so I have to shift it left to bring the center over. So that's why I'm subtracting that distance. And then, so that's my x value from the center. Makes sense, right? Because the x value here from here is going to be bigger than if I measured it from there. So that's why I subtract. And then a squared is up here, and now the y values, since it's centered about the x-axis anyway, the y coordinate of the foci and the center are all the same. So I don't have to shift that one. And so I can do this for every single point. And remember, the goal is we want them to all equal 1. But they don't. But look at that average value. And that's pretty close, right? I mean, right then and there, I could do a % difference from 1. Although, the way I've set this up, I bet you get the same thing. So the standard deviation of the sample, remember, that's a characterization of how much the data wiggles back and forth about the average value. So notice that if I put this into as above, as a number, and I give it the same number of decimal places, you notice that it's 0.01 against 1, so it's 1/100th basically. And not only that, that's just the variation of the data, but at the end of the day, I can quote the standard error. And in fact, this is 20 values, but I tell you there's a better way to do this. And we're going to use this command, and I think we've used it before, a command called count. And that way I know that I know exactly how many, what there are there. And then I simply take the relative error, which is the value, the standard error divided by the value, which is true. It's the plus minus divided by the value. I multiply it by 100 to get 0.3%. So look, we are happy if that number was 10%. So we've demonstrated Kepler's first law because we have these parameters of the fit to the data, the A, B, the C, and the E. And so we were able to then determine where the center of the ellipse is. We took all the XY points of the data, not the fit, and we shifted them so that they reflect the center of the ellipse. And when I put that all into my equation, I got an x squared plus y squared that wasn't exactly 1 every time, because you see the fit wavers a little bit. And if you look at the blue line and the red line, they don't, sometimes they're on top of each other, sometimes they, see, the blue line is actually, a red line's inside, and here it's outside. Yeah, I'm going to try 53 degrees there. I bet you that's going to work, but you don't care. So I took the average, and just because the average is 1 doesn't necessarily mean I have success. It's the very tiny variance and relative error that's what really seals the deal. So now we have demonstrated that Toro obeys Kepler's first law, which is what we expect. And, right, so there you go. Now, area. Kepler's second law says that equal areas are swept out in equal times. So we know each of them is a 30-day interval. And so then we know that the delta theta for each one of our little pi wedges, if you will, which is just simply if I drew, well, let's go take a look here. And I got this toolbar in my way again. And let's see, where is the line? Insert a line. Shapes. So basically, a pi wedge, and remember, it has to be from the focal point. Well, you may not know that. I'm telling you. Although you should make sure you understand that one. And I need another line. So this is a pi wedge, for example. And I can do that all around. And then the original lab wanted you to count the little boxes. But I finally figured out how to do this. And let's get back to the manual. So this isn't exactly a triangle, but because if I keep delta theta small, I can assume that this this is a straight line. So we know the length of this arc in general is just going to be r times the change in angle. And so I put the theta 1 and theta 2 and r2 and r1 because, and maybe I should have used final and initial, because we have for each of our points on our ellipse, right, there's a theta value and an r value. Now, this is a triangle, and the basic, if I assume this is a straight line, it's a triangle. And yes, a little bit of error is introduced. The bigger is the delta theta, because that arc length becomes a little bit longer. The straight line from these 2 points is called a chord. And on top of that, we have another source of error because the radius is not constant. It changes over the interval, but we can use what we've used before, where if we keep delta theta small enough, R1 and it won't change very much from R1 to R2, so we can use the average value. So notice that also, I guess I could have also said equals to 1/2 R squared delta theta. So we're going to use 1/2. That's the average of the two. And I have final and initial because you're going to do it over and over again. And square it and delta theta. And yes, this gets us to be completely precise. This equation gets the area of a pi wedge. But we also know that except for points 20 and 1, any pair of these points, the time between them is 30 days. All right, so let's see here. There's my equation. It's the average of the two radii. And then it is the, I see F11 minus F10. That's the delta. Oh, yeah, and I squared the average radius. There's my 0.5. All right. And just notice that, see how it progresses. Now it's the next pair, right? And it does that automatically for you. And notice, though, we only get 19 of them. Now, one of the others, if the radius of these two varies too much, that introduces error. And you can kind of see that these things, I haven't graphed them, but they dance up and down a little bit. So they do have some variance. So once again, we can take the average. Now, one thing I want to show you, what I did here, is that I just took these and I dragged them across. And so now you notice that there's a blank box. So, but I can just grab that blue, and then here, once again, I just grab that blue, then move it, enter, and this one is partially taken care of. Oh no, it's not. See, that is going to change a lot. And there we go. And of course, we don't know what this is yet, but same thing though. That's a pretty nice feature, and I only just discovered it recently. And let's just get it back. All right. So anyways, I take the average value, and that one, it's not as meaningful as looking for the number 1. But I go here and I look at how much it varies, and once more, it's about 1/100th. And then I get the standard error, square root of the number of measurements, and then I get the relative error, and again, in percent, it's 0.5%. So, as far as I'm concerned, they're all consistent. Now, one thing I was a little worried about was, to me, that's success, right? So what I went ahead and did, it was very tedious, but and you don't have to do this. I wanted to see about if I divided each pi wedge into 10 slices, and Excel has trouble doing that. And so, and I don't know what's going on here. because, yeah, the fit equation is different now. So I have to copy that and paste it. Now it has a number. All right. So this is where the fit equation came in handy. And in principle, what I could do is integrate the fit equation, but that is a bear to integrate right there. Because if you do an integration, the integration gives you the area of this pi wedge. So, but that's a pretty nasty thing to integrate. But I can still do it with the average value thing. And so you see I have now, these are, let's see, these are angles. And what's going on here? Oh, yeah. Here it is. So then we have the average value squared, the delta theta. So I calculate the radius and at 10 values across the pi wedge, and then I sum them up. And there is the final answer. And so I did that, and when I do that now, so I take this and copy it, and then paste value for each interval. So this is the last one here, see? And so then that's the 3.35. And I really was surprised that at the end of the day, when I did the average and the standard deviation, the variance, and the standard error, that I ended up with a somewhat larger relative error. I really thought it would get smaller. Really interesting, right? So someday I'll do an actual integration and calculate the value directly. Okay, so let's go back. What else do we have now? The third law. So predict note. So I rearranged this so you guys can do this yourselves with a calculator, because now we know A, and it says to express RA, don't forget, is expressed in astronomical units. So that's why you would plug it in here. And then you would get, it depends. If you type in 365 here or type in 1, then you get the number of days in directly if you put 365, or you'll get it in a number of years, and then you multiply by 365. In fact, Earth's period is 365 and a quarter, by the way, but that's discussion for another day. Okay, so check the prediction. We did this in class. That recording is, well, it's around, but I'll reiterate it for you, because now with all this fit data, it becomes pretty easy. Okay, so count the number of 30-day intervals. So you see 1, 2, 3, 4, etc. And then you multiply that number by 30. I forget the number off the top of my head. Now, we need to estimate how many days are in the interval from 20 to 1. And let's see, take the average value, get the number of days, calculate for interval 1 to, okay, yeah, and get 20. Now, to get the number of days that go from point 20 over to point 1, get the average value, let's see, remember delta t equals 30 days. So what I want to do then is I want to get the delta theta over delta t for these two intervals, the interval from 1 to 2 and the interval from 19 to 20. Yeah, that's what it says. And don't forget, we have that in the first one here. We constructed that already. And so that says, where is it? Delta theta, here we go. So we get 0.099. And then for the last one, we got 0.007. So then we could just get what's the average of that? And that will get us a number for use for that interval. So equals this. Oh no, I want to do average. AVE or AGE. And so, yep. And then we put a comma. And then the last interval. Bingo. And we see it's 0.039. And then we need to know what is the delta theta for, sorry, 21 minutes to copy, paste. The delta theta for 20 to 1. And that's going to equal to, we got to be careful here because that is at 7.156, right? Which we have to convert that to, once you hit 2 pi, then that's got to recycle. And so then that is, this is, oh, right, of course, 356, but I add 52 degrees, so I'm past 360. Okay, give me a minute here. The radians, yeah, all right, so I need to know what is the theta position of 20 in minus 2 pi. And so that means, okay, yeah, I know what to do. So from 20 to 1, the final position is the number of radians for 1. And the initial position is going to be the number of radians at 20 minus 2 times pi. And that's just pi, open parentheses, close. And get it? So that means that the number of days in that interval is going to equal this times this, and for some reason I don't like that. I'm going to pause for a moment. Okay. Obviously, I'm pretty tired. It's almost 6 p.m. I've been here in my lab all day working hard for you guys. So, and I noticed I clicked on this box over here instead of these two. So the average radians per day is 0.0085. And then I took the value at 0.20 and I subtracted 2 pi, 1 full circle. Then I did the difference from the final position is 0.1 minus the position at 0.20 where I started, which is the above there, so the blue and the up to the left. And then I was multiplying, but you need to divide, and the reason is that I have a number of radians, and I want days, and so then I have a radians per day, When I divide, then it's then the radians cancel out. So I get that, and so well, let's see. I know that there's 19 intervals. Well, I'll let you guys do that part. So it's a somewhat different number than we got in class for the other day. I don't know what's the difference here. Point oh. I think we just refined some values, but I believe this one more. Okay, so let's go back to the manual and so I've just about had it here. I'm gonna stop this one. Okay, I just realized that I didn't have to really stop that because it's only a little bit longer to go. Let's see. So you get in step 3, you get a number of days. Step 4, you get a number of days. Okay. So this last one here, I just realized you don't need the spreadsheet. Well, you don't need to do a calculation. So this one is saying that the period of Toro in days should be equal to the total area of the ellipse divided by an area of a wedge, for example, because you know each wedge is 30 days, right? So that makes sense. And then, of course, you need the 30 days here, this ratio. So to get the period of Toro, you just take this guy here and bring it up to here. So in your calculator, you know you can get A and B from your spreadsheet. You got an area of wedge there. I mean, heck, can you just use the... I think you can just use the average value, right? Yeah, because that's an area of the wedge. That's every one of the wedges. So you can use that. And you know A and B. That's in your fit parameter table up here now, right? There's your A and B. And then you just make that the total pi AB divided by the average value of the area of wedge, and then multiply it by 30, and you get the period of Toro. So now you can compare that to 3 and 4. And then the mass of the sun, that's great. So once you know the period of Toro in days, you can convert it to seconds. And then A, you need to convert it to meters. And because remember, our A is in AUs. Oh, let's see. Would it work if we used AUs up here? Oh, let's take a quick look. Yeah, because we used the radius in AUs. Okay, good. So AB will get us the area in pi AB will get us the area in AUs, and then this will get us, you have the area in AUs both ways, because A and B are in AUs. But now you have to convert that one of those. I don't know which one is the more accurate. That's funny. I don't know. I guess basically I would use, me personally, I think that using this one, Kepler's third law, and then I would convert it to seconds. It's squared. I guess I should have put it there. And then A is in AUs, so you convert that to meters. And then you have to solve for, right, because I'm going to assume you guys know how to do that, because if you plug all these numbers in, and well, anyway, you got to solve for that. I'm shot. I'm just going to tack this on to the video, or the last video where I said I'm going to stop it now. Okay, I'm going to pack up, go home, and start uploading these. See you soon.